Back to another video, and this time we're going to be looking at type 2 improper functions. Improper integrals. Okay. So, we've done type 1, and that's from where we have one end and then an infinite end, right? And that's where we find the limit. Well, type 2 improper integrals is just when we're doing it instead of infinity, right? A to infinity. Instead of that, we're doing it to an like a discontinuous point. So if you imagine a graph where it looks like this, where the curve looks like this, right? And this was A and B. You see how the whole function here is discontinuous at the point B. So if we wanted to integrate it, we basically do the same thing as integrating from A to B, but you just have to use limits just to be mathematically correct. And so the way we denote it is if for example it was discontinuous at B, just like I drawn B, then we want to do from A to B. So if it was from A here, then the integral from A to B would just simply be the limit from t to b from the left side, because we're going on left side from a to b, right, from the left side, that minus there, and then this integral. Or if, for example, the equation was instead discontinuous at a, right? Let's say it was a, this is function. Well, then we're going left to right to left, and therefore, if it was discontinuous at a, it would just be lim t a to the from the positive side, and tb like that. Okay, and another quick note is if it was discontinuous in the middle between A and B, we want to find the whole total volume. Well, all we got to do is that we set it up so that it's from two different things. So from A to C, and then you approach C from the right side using lim t, and then from C to B, we approach sorry, why did I write it like this? From C to B, where you lim from C from the right side. So that's just how it works. Let's do a few examples. And oh, I forgot to tell you, if the limit exists, then it's convergent. If it like ends up being infinity, then it's divergent. So similar thing to what we did with type 1 improper integrals. It's really simple. So let's do one first with this example here. So from 1 to 3 of 1 over square root of x plus 1. So let's do this. So the integral from 1 to 3 of 1 over the square root of x plus 1. Sorry, it should be x minus 1, right? Yeah, x minus 1. Okay, so where's the limit here? Where's the discontinuity? So if you see here, at 1, x is going to be, so x is 1 minus 1, that's 0, square root of 0, 0. So what we're going to end up with is 1 over 0, which is impossible, right? That's undefined. So it's actually incontinuous. It's going to be like some kind of exponential graph, and this is going to be, sorry, it's going to be like a reciprocal graph, and this is going to be at 1. This is the function, right? But that means that it's going to be discontinuous there. So how are we going to find the limit for this? Well, simple. Going to set up just like we did for before with type 1 improper integrals, and we do lim t to 1 from the minus side, the integral from t to 3 of, and let's rewrite this as x minus 1 to the power of minus 1. That's it. And it's just a simple process of doing the integration. So let's do this really quick. Lim t 1 from the positive side. Sorry, why did I do this? Positive side. And the integration of this is going to be increase the power by 1, divide by the new power, multiply it, and then it's just going to be x minus 1 to the power of 1/2. Just the square root. And that's going to be from t to 3. Okay, so let's do this. So we can expand this and we can say that this is going to be 2 multiplied by 3 minus 1 to the power of 1/2 minus, and this is the limit here, lim t of 1 from the positive side of 2 t minus 1 to the power of 1/2. The reason why we're writing lim like this is just so that we can get it mathematically correct. It is correct just to substitute 1 to the equation, but this is just to prove it mathematically. Alright, guys. This is simply going to be the 2 root 2 minus, and here we're going to take 2 out, and 2, that's just the rule of limits. You can take the constants out. So now what we have here is, and then we put the 1 in here, so it's going to be 1 minus 1 to the power of 1/2. And 1 minus 1 is obviously 0, and so this 2 gets canceled out. Therefore, the limit is 2 root 2. And therefore, we know that this is a convergent improper integral. Okay, so next, example, we have this one where we have the integral from 0 to 1 of ln x dx. So this one is interesting, and you're going to see why. So let's do 0 to 1 of ln x dx. And if you don't know the integral of, actually, let's do this really quick. Let's rewrite this. Let's think about it first. So what does the what does the ln x graph look like? It looks something like this, where it approaches 0, x equals 0, but it can't reach it, right? And that's because ln x is the inverse of e to the x, and e to the x can never get 0, because e to the power of something can never be 0. It just goes closer and closer to 0. So technically, ln of 0 would be negative infinity, but we're going to get there. So let's rewrite this as ln to be mathematically correct. This is because 0 technically doesn't matter, it doesn't exist when you integrate it with ln. So we're going to have t approaches 0, since we're going from 1 to 0, so that's going to be 0 from the positive side. The integral of t to 1 of ln t dx. Ln t. Why did I write t? Ln x dx. And, okay. So lim of t to this, and then let's do the integration. So this is still going to be lim t to positive 0 from the positive side. We're multiplying this. The integral of ln x is simply x ln x, x ln x minus x, just by integration by parts, and this can be t and 1. And what you're going to end up with is something that looks like, let's do 1. So 1 multiplied by ln of 1 minus 1. Okay, now we're going to minus it again with t in it. So minus, it's going to be lim t to the positive 0 of t ln t, and then plus lim from t to positive 0, 0 from the positive side of t. Okay, so this one obviously goes to 0, right? Substitute 0 in, that's 0. Ln of 1, that's also 0, because e to the 0 is 1. So this one goes to 0. So what we're left with right now is minus 1 and minus lim of t to 0 from the positive side with t ln t. So let's look at this one. Ignore the minus sign for now. And let's look at what this looks like. So what we end up with is, if we rewrite this, right? This is technically impossible. What you're going to get is 0 multiplied by negative infinity, because ln 0, as we've shown with the graphs, is negative infinity, which doesn't really make sense. And so what we want to use is L'Hopital's. L'Hopital says that if you have a function where you have like infinity over infinity, or 0 over 0, or infinity over 0, then you can use L'Hopital's. So what we want to show is somehow be able to reach that. So let's see. Let's rewrite this function as lim t to 0 from the positive side of ln t divided by 1 over t. Does that works, right? And if we substitute 0 in, what we end up with is ln 0, that's just negative infinity, over 1 over 0. 1 over 0 is just infinity. So now we have infinity over infinity type. Use L'Hopital's. Okay. Use L'Hopital's. Okay. Let me add another page. So if we use L'Hopital's, we're going to have to differentiate both the top and the bottom. So let's do that. The differentiation of, so what this end up with is d over dx of ln t over dx of 1 over t. And keep in mind that this is still using the limits t to 0 from the positive side. Okay, so differentiation of ln t is just 1 over t. Differentiation of 1 over t, which is the same as saying differentiation of t to the minus 1, is going to be minus t to the minus 2, which simply we can arrange it as 1 over t squared. Okay, in this case, this is still lim of t to the 0. Yeah, I know it gets tedious. So yeah, and then, fraction division, that's going to go up. So it's going to be minus t squared over t, which means you can cancel that out. So lim t to the 0 of minus t, therefore that's equal to 0, because minus t, we put 0 into t, that's minus 0. So what we end up with is minus 1 minus 0, and 0 is like that. Therefore, the integral of this is minus 1, and therefore this is convergent. All right. Sorry for the amount of work that was. Thank you guys so much for watching. I'll see you guys again.